attending the Second International Non-Conventional Energy Technology Symposium in 1983, Meeting of the Minds in 1987, the Learned Sufferers also in 87, the American Nuclear Society in 1989. He's published several articles in Roundsight and Magnets magazines. So let's please welcome Paul Brown.
Here's your tie clip. This thing has fallen out once now. We know that, so
I'm sure it'll work.
Yeah.
Good. Okay. It's almost ludicrous for me to have wore a suit today. Most people have seen me run around in casual attire for the past couple of days. I'm going to cover a lot of material, so I'm going to read from a script, and we'll go through some slides. The subject of my talk is Tesla technology and radioisotopic energy generation. The basic electrical resonance principles pioneered by Nikola Tesla in the late 1800s are now being applied to a method of generating electricity from natural radioactive decay. NuCell Inc., a subsidiary of Peripheral Systems in Portland, Oregon, received a patent in May 1989 for their resonant nuclear power supply. In general, the resonant nuclear oscillator is an LCR tank circuit tuned to oscillate at its self-resonant frequency. Energy in excess of the operational losses is contributed from a radioactive source to the tank circuit through a phenomenon known as the beta Voltaic effect. Net electric current is then removed from the oscillator through an impedance-matched transformer to deliver high-frequency electricity in usable form to drive a load. The beta Voltaic effect may simply be defined as the conversion of ionizing radiation to electrical energy by a material or a combination of materials. Any radiation that is absorbed in the vicinity of a potential barrier will generate separated electron-hole pairs, which in turn flow in an electric circuit in response to the influence of the electric potential field. Radioactive decay energy is orders of magnitude greater than chemical energy. For this reason, this technology has the promise of yielding low volume, low weight, high energy density power sources that will be economical for long unattended life with high reliability. Devices for converting natural radioactive decay directly into electricity are nothing new. The beta cell, figure A here, was first demonstrated by Moseley in 1913, and over the years many types and methods have been developed. This technology has been made possible due to the electrical nature of alpha and beta disintegrations. Figure A is radioisotopes are random in their electrical disintegrations. However, all those disintegrations do go away from the radioactive source. So if you simply put a conductive sphere around your radioactive source to collect those charges, whether they be alpha or beta particles, you will have a difference in potential established. These devices have been built as large as 2 kilowatts by RCA. However, they're very inefficient. They're very high voltage. The largest ones were built at 1 million volts, but of course microamps of current. Figure B is a secondary emission type cell. The difference between it and a primary cell is rather than having primary beta particles absorbed by your electrodes, the radiation is actually absorbed in a gas to produce secondary electrons. The benefit of generating secondary electrons is that you get a greater number of charge carriers. In the nuclear battery field, that's referred to as the multiplication factor of the cell. So this type of device has a greater current and will operate at a lower voltage, but they also suffered from efficiency problems. Figure C is in the early 1970s, Paul Rappaport, again with RCA, discovered that if you irradiate a p-n junction transistor with a beta source, that the cascading effect of the beta particles through the silicon create, again, secondary electrons. That cascade of, so long as that cascade of electrons goes across the junction, then current will flow. These had a lot of promise in the early 70s to be used for pacemaker batteries. That came to an end in 1974 when the lithium cell was introduced. But these devices also suffered from short life. When they work very well, but they don't last very long. The beta bombardment destroys the junction. Anyway, and then of course D is the type of nuclear battery that's been in use since 1963. It's called an RTG for short. That stands for Radioisotopic Thermoelectric Generator. And basically how that works is radioactive materials, due to self-absorption, are always hotter than their surroundings. So if you have a lot of radioactive material, you have a heat source. Simply by placing a thermocouple about the heat source, the thermocouple converts the heat into electricity. The technology is very simple, it's reliable, but unfortunately it's not very efficient. RTGs are very large. Typically, because they're using waste heat, they're limited in the radioisotopes that they can use. However, they have been applied. Voyager, Pioneer, just about every deep space probe got an RTG for power, because solar cells won't work that far away from the sun. The Apollo program took SNAP 27 generators to the moon to run their electronics packages that were left behind. Several communications and military satellites also powered by RTGs. This is a brief list of patents that have been issued for these classes of nuclear batteries. However, the simplest form of nuclear battery is the Burke cell. This method consists of a conventional battery and a conventional load connected by means of a radioactive conductor. If we inspect this arrangement, we find that all the power dissipated in the load is not drawn from the battery. And upon closer examination, we find that a current amplification occurs within the radioactive conductor. This phenomenon is known as the beta Voltaic effect and may be explained by referring to this next figure. I want to point out that the shortcoming to a Burke cell is that it does require a battery, so it also has limited life. Okay, for the simple case of this example, we'll set the radioactive source, being any alpha or beta emitter, external and separate from a silver wire. Now the battery from the previous figure provides an EMF across the wire, and consequently conduction electrons within the wire are set in uniform motion. By definition, electricity is measured in terms of the number of charged particles or electrons moving past a point in a unit of time, and we call this amps. The process by which a beta particle is absorbed is such that the beta particle collides with the molecular structure of the copper, knocking electrons free. This electron avalanche occurs until the beta particle, which is an electron, effectively comes to rest. A single beta particle emitted from strontium-90 that is absorbed in copper will generate 80,000 ions in a distance of 30 thousandths of an inch. Now, as soon as these electrons are knocked loose, they effectively become free electrons in the wire, and as such, these additional electrons are acted upon by the EMF applied across the wire to give the avalanche electrons a uniform direction of flow, regardless of their incident angle. This increase in the number of moving charge carriers is measured in the real world as increased current. We also measure a reduction in the resistance of the wire, an increase in its conductivity, while the current is directly proportional to the voltage. In other words, the current goes up with an increase in the voltage. This is basically attributed to the increased EMF acting on a greater number of avalanche electrons. This is a cartoon representation of the basic beta-voltaic converter. Electrode A has a positive potential while electrode B is negative, with the potential difference provided by any conventional means. An electric field exists between the electrodes, and we shall call this zone the junction. The junction between the two electrodes is thus comprised of a suitably ionizable medium exposed to decay particles emitted from a radioactive source. In general, the introduction of ions from any source into an electric field will generate electricity in accordance with well-known physical and chemical principles and may be satisfactorily explained in terms commonly associated with the beta-voltaic effect. The energy contributed to such a circuit does not come from the ions themselves, but rather from the work done on the circuit to generate the ions, known as the ionization potential of that particular material. An amount of work must be performed on a neutral atom to remove its electrons. This work manifests itself as increased potential energy and may be utilized to do work before allowing the electron and ion to recombine. Neither the electric field, the electrodes, or the medium between the electrodes contribute any energy in the beta-voltaic effect. The energy is contributed by the ion generator. Whether this mechanism is chemical, electromagnetic, or nuclear is irrelevant. In other words, assume the conductor is irradiated with beta particles, and as these particles penetrate the conductor, collisions occur with the electrons in the lattice of the conductor, resulting in the transfer of energy to these electrons and exciting them to a higher energy level in the conduction band. Okay, now we'll look at how we apply this phenomenon to our device. Here we have your basic LC tank circuit comprised of an inductor and a capacitor. Theoretically, if this LC circuit was superconductive, then an externally applied electric impulse would yield an LC oscillation that would continue to oscillate forever due to no losses in the system. However, our LC circuit is not superconductive, and the oscillation damps out due to the losses inherent in the LC tank. To minimize these inherent losses, we tune the circuit into resonance at the self-resonant frequency of the inductor. This causes the inductive and capacitive reactances to cancel, leaving only ohmic losses, that is, resistance. Now, if we apply a radioactive source as part of the LC tank, then through every cycle of the oscillation of which current is flowing, that current gets amplified by an amount proportional to the activity of the source. All we need is an input of an amount of energy equal to the system losses to achieve a sustained oscillation. At this point, we have a self-driven oscillator that we call a nuclear-powered oscillator. Any energy contributed to this oscillating LC tank must be removed, and we accomplish this simply by impedance matching a transformer, which yields high-frequency AC current to drive a load. In a nutshell, that's the principle of operation for the resonant nuclear power supply. It's an LC tank circuit oscillating at self-resonant frequency, driven by natural radioactive decay energy. Energy in excess of the operational requirements is removed through a transformer to yield electrical energy in usable form to drive a load. Here we show the starting method, which involves the use of a high voltage source to charge the capacitor in the tank circuit, which is then discharged to ground through a Class C amplifier at a rate equal to the resonant frequency of the tank circuit. A spectrum analyzer is used to monitor the activity within the tank, and once a clean oscillation is started, the high voltage power supply and the Class C amplifier are removed. This process takes only a few seconds. Then the power removed from the tank circuit is determined by measuring the voltage drop across a resistor of known value and double-checked by directly measuring the current delivered to the load. That has been the process we've used in the past. What we're currently doing for more precise measurements is we're using calorimetry. The great attraction of radioisotope generators lies in the fact that isotopic energy densities are several orders of magnitude greater than chemical energy density. However, the technology currently used for radioisotope power generation is severely limited by its low efficiency, isotope limitations, and heavy shielding requirements, while a resonant nuclear generator does not suffer from these limitations. Here we have an actual component layout of an early prototype. This was actually our proof of feasibility device. Here we see the radioactive source. This is the radioactive source here. It's in a foil form. It's on an aluminum mandrel. Okay, and of course the radioactive source is on a mount, and the primary inductor is low and to the right, kind of a whitish coating on the outside, and of course the matching transformer, which some of you will recognize as resembling a Hubbard coil. Unfortunately, the tuning capacitors aren't shown in this picture. There was a prototype before this where everything was built inside, but for testing purposes, we decided to bring all the electrical connections external to the device so that we wouldn't have to be continually putting it together and taking it apart. And that's the large plug over to the right that you see all the Teflon-coated wire coming to. Anyway, here we have, this is the actual wiring of the prototype shown in the previous slide. Although this generated electricity, it also demonstrated a frequency stability problem and showed signs of material degradation. By the way, this generated 70 watts of power for a period of about 3 weeks before the frequency stability problem shut it down. Economic studies indicate that a radioisotopic nuclear battery is economically competitive with chemical batteries for applications requiring lifetimes of over 2 years at remote locations where the expense of charging or changing batteries is significant. Applications where the inaccessibility after implantation is a consideration that leads to selection of nuclear batteries due to their superior reliability in life. We've pursued several design variations and are currently working with an independent nuclear engineering firm. Our current program will generate engineering data in the coming months. Of course, any alpha or beta emitting isotope will work, while a design variation also allows the use of gamma sources. We have experimented with cesium, strontium, radium, krypton, tritium, promethium, and probably some others I'm excluding. But all these sources have worked. However, for personal safety and application considerations, we're currently planning to use Krypton 85 as the fuel source, although strontium-90 is still a good candidate. Large quantities of Krypton 85 are contained in stored power reactor fuels, and about 1 megacurie per year is available from processed fuel. It is estimated that 42 megacuries of Krypton 85 could be obtained from existing inventories in power reactor fuels, with the content in spent power reactor fuels at about 8,500 curies per ton. Of the many radioactive isotopes generated by the fission of uranium, Krypton 85 has many unique properties, of which the most important is its advantage of being environmentally the most acceptable radioisotope available for power production. Preliminary data suggests that energy densities on the order of 1/4 watt per cubic centimeter is achievable. Market surveys have been conducted by the nuclear industry in the past, and the conclusion has been that there is a need for long-life radioisotope nuclear batteries. Of course, economic and logistical factors must be considered for comparison. Obviously, the physical size and shape of the radioisotope batteries will need to be related to the intended applications. For example, in oil and gas well drilling, there is an increasing benefit in continuously measuring and monitoring geophysical data from the bottom of the hole. Under these circumstances, it would be necessary to accommodate a battery within the diameter of the drilling tubes. Another important potential market is to supply long-life electrical service to the sonobuoy detectors, which are in locations throughout the oceans of the world. The overall configuration in this case would probably be quite different than the previous case. All these possible applications need to be considered throughout the development phase. Based on application surveys, a design and development testing program is being conducted on novel radioisotopic batteries that would be economical for long unattended life with high reliability, low weight and volume in the power range of 10 to 5,000 milliwatts. Our first 5-watt model is the size of a D cell, has a 5-year working life with a 10-year life expectancy, and we should be production ready by January. Give you these are some of the early prototypes. We have built very large prototypes. We've as large as 50 kilowatts. This is just a little quick pictorial tour around our lab. Lab's located in Portland, Oregon. This is our hot cell area. We have beta box in the back corner. Is also a gamma box. You can just barely see the remote handles sticking out from it. And of course, on the other side of the room, we have scintillation equipment, multi-channel analyzers, and NBS traceable sources. Here in this picture, you can see that on the spectrum analyzer that this device generates a very strong 50 kilohertz, very clean signal. The noise floor depicted on the spectrum analyzer is just as the noise floor. We didn't delete that. And of course, on the scope, you can see that it's a very clean. This is a voltage current comparison. You can see that the voltage and current are in phase, and that the oscillation is very clean, which is also suggested by the analysis on the spectrum analyzer. This is some other stuff that we'll skip that. That's for beta conductivity gain, part of the mathematical model. I can answer questions for just a few minutes, and then I understand we want to be sure everybody gets a break and a chance to get checked out. Sure.
You had a gas-filled gas strip cylinders mounting power supply. I saw a bell on the exterior.
Oh, very much so. We ran a lot of experiments with a vacuum and various gases. What we're currently using is pressurized xenon. We're putting xenon in, stable xenon, at about 200 psi. It works as more as an insulator than anything else. We have had ionization problems in the device. The primary tank in that device that was shown was 10 kV. Yes?
I have two quick questions to make.
Okay.
Now, the first strikes me is you said you produce 70 watts. In another case, you said you produce 50 kilowatts out of the radioactive material source.
That's right.
Now, this sounds to me too much there. Because if you transport the radioactive material, that means always is producing 70 watts. You should see the case burn with 70 watts. Is that so? I mean, 50 kilowatts. How did you transport the radioactive material which was producing continuously 50 kilowatts before putting into your device?
How did we?
You have a cooling mechanism?
No, we don't have,
Power is always emitted there.
well, we don't have a cooling mechanism. That's part of the reason that the large devices are not production ready, is that we have some technical issues that remain to be solved.
When you turn off the device, the energy still comes out from the source.
That's true.
And that 50 kilowatts still will come out. And
I've got to point out that we don't turn off the device. The nuclear batteries run at their full power at all times, whether you use them or not.
During the time you install the thing, it will burn it. 50 kilowatts is installing before turning on the machine to consume the energy there.
It requires special handling equipment. I admit.
It sounds over unity here.
No, it's definitely not over unity. It can be explained within the context of accepted physics.
Something I don't understand here. The other thing that's not clear to me, you mentioned when you radiate a wire with the beta decay, with the beta radiation,
I assume everybody can hear this.
you induce...
No? Okay. I'll repeat the questions from now on. I'm sorry. Okay, go ahead.
You induce a voltage there, an EMF.
No, we do not induce a voltage. The EMF is provided from an external source, in this case the capacitor.
But it helps the current, so you are
Yes.
not an extra EMF. You are adding a second EMF.
Not in that. Okay, the question was in the explanation of the ionization of a wire that we're inducing an EMF in the wires from beta bombardment, and my answer is that that's not correct. The EMF is being provided from an external source, as in the Burke cell. The EMF is provided by a battery. The absorption of the beta particles give up their kinetic energy and generate electron hole pairs.
All right, but you are offering energy there. You are helping the current, in other words.
Definitely, yes, we are helping the current.
Now, the thing is that you are bombarding something that's statistical with electrons, which are all directions. We are bombarding perpendicular. And then that ends the flow, which is in one direction.
Right.
Is this your interpretation? Is it the standard phenomenon in the literature? I never know about it.
Okay, the question is this phenomenon standard, or is it my interpretation? The beta voltaic effect is a standard and well-known phenomenon. Was first detected about 1906. Was well documented by Marie Curie, Becquerel, in its initial stages, and several others over the years. It's been
using a current. You radiate the wire that produces a current. Why produces the current that way and not the opposite way? What makes it this way and not the other way around?
Okay, the question is what provides a uniform motion to the cascade electrons?
Disorder to order. We go from disorder to order.
What produces the uniform motion is the EMF present. It's the force that turns them all in the same direction.
How is that?
An EMF is an electromotive force, and any charged particle in the presence of an EMF reacts according to well-known physical principles, so that the end result is that you get a uniform direction of flow.
Well, certainly half of the cycle, the capacitor is the battery supplying the EMF. The other half of the cycle, the inductor, the field collapsing through it, is supplying the EMF going back the other direction.
Very, very much true.
And the current multiplication is going on both half cycles, both directions of the wire.
Exactly. That's why I pointed out that the statement is that in one cycle the capacitor provides an EMF, and in the other half cycle the inductor with the collapsing magnetic field produces the EMF. And so that you have a contribution of energy through both half cycles. The contribution of energy is there so long as an EMF is present, and there are 2 points in each cycle where there's no EMF present, and only during that period is there not an energy conversion.
It sounds that what you have is really an electrical laser In other words, think of the wire like a tube of ionized gas, and the light that triggers a coherent release of energy. Pretty soon you have a photon cascade going all the same direction. Similar to what you have here, the current, initial input current is triggering the alignment of all these electrons to flow in a similar direction.
It wasn't a question really so much as a statement that an analogy to a laser could be drawn because we're culminating a beam effectively of charged particles, which is effectively correct, yes.
Is your oscillator frequency inversely proportional to the count rating?
No, the oscillator frequency. The question was: is there a link between the oscillator frequency and the nuclear decay? And the answer is no. The oscillator frequency is determined by the physical parameters of its assembly, meaning that we could change the frequency by simply taking a few turns off of the transformer or the primary inductor. Yes.
The cascade releases all these free electrons. Doesn't it also create a bunch of holes? And why aren't those holes absorbing the same number of electrons as you just freed?
Okay. The question is in this cascading effect, are not electron-hole pairs generated, and why don't the holes absorb the next electron that comes along? Well, the answer is that's exactly how electricity works. An EMF kicks an electron out of a hole, moves it down a line, and the next electron comes along, falls in the hole. As long as you have a migration in the same direction rather than random, which is random production is a thermal effect. As long as the production has a uniform direction of flow, then that's an electric current. Yes.
A couple of questions, both of them economic.
Okay.
The price on the little 5-watt D-cell version of this battery is anticipated to be approximately what? Okay.
This is a very cost-effective device. The materials are cheap, including the radioisotopes. However, our initial production will be pretty spendy because we have to recoup our research investment. That's primarily why our first market is military. And the exact price hasn't been set yet, but it's going to be in the ballpark of about $5,000 a piece. This compares with the military and NASA are currently spending $500,000 a piece for an RTG. So we can offer them an extreme savings. However, we do not, in limited production, we plan on making these ourselves, but we don't kid ourselves. We aren't in a position to go into large-scale production, so we will team up with somebody, Westinghouse, GE, somebody like that. I can't say who at this time.
The other question
Okay.
I have is, wouldn't an enlarged, enhanced version of this battery be a possible way of putting a lot of the reactor waste to use? There's, of course, a lot of griping and bitching going on about nuclear waste. Wouldn't this be possibly a route to turn that into usable material instead of something that has to be buried?
Okay, the question was couldn't larger versions of this device be utilized in a useful way to use waste radioisotopes? And the response is that yeah, that's why we're very excited about our product, is that we have a technology here that turns waste radioisotopes into a useful commodity. And by no means, because we've targeted this 5-watt device as our initial commercial product, are we going to forget development on the larger ones. We definitely want to pursue those. But anyway, the answer is yes. This does provide not a complete solution, but it will help the problem. Yeah. Yes.
All right. Well, if you had a pure alpha emitter versus a pure beta emitter, would the alpha emitter give you as much energy output as the pure beta emitter, assuming they emitted the same number of particles?
Okay. The question is
Can it be utilized?
Oh, okay. Well, the question is will an alpha emitter work as well as a beta emitter? And the answer is that alpha emitters work much better than beta emitters, but there are some long-term design problems involved with all the alpha sources, in that an alpha particle is a helium nucleus. So after it's absorbed, it picks up a stray electron and floats away as helium. That means if you've got a sealed device, you've also got a helium generator inside that will build up pressure over a long period of time. So eventually it will develop a leak. There is surely a method of venting the helium, but that method is not currently available or not in an acceptable manner anyway to the NRC. Well, like I say, there would also be a limit to the palladium. It would saturate at some time. Yes?
I was wondering, for every centimeter of wire, or whatever from emitter, how much current do you put in?
Okay. Per unit, the question was for every centimeter of length of wire, how much current do we contribute? I don't have that answer off the top of my head, but we could get that information for you from our notes. It wouldn't be tough to difficult, because it wouldn't be too difficult to calculate, because it would simply be the 1/2 of the surface area of our silver ribbon times its length, and the current. So I could come up with that number, but I don't know that off the top of my head. Yes.
We talked about this a couple of years ago. I got the impression that since you were a little bit less business-oriented at that point, you were considering the home unit, whereas more people that are connected to the utility as you get into the profit motive, could you keep in mind our needs for disconnecting to the utility company at some point?
Okay. I think everybody heard the statement. And as he said, yeah, we've built some large units, and that was and still remains my hope is that we can utilize these not just for home electrical systems, but also for electric vehicles. Something I have to point out that I really didn't go over entirely in my talk was the safety of Krypton 85. Krypton 85, I must stress, it's a clean beta emitter. It decays directly to stable rubidium by beta emission. There's no gamma rays present. It's such a low energy. There's no bremsstrahlung production, bremsstrahlung being secondary X-rays. It's an inert gas. The process that we're using in our device is it's a sputtering process where the krypton gas is actually deposited into the metal matrix of nickel. The only way you can get the krypton out is to heat the nickel above 700 degrees C. In the event you did get it out anyway, because it's inert, it does not present a biological hazard. If you were to ingest this material in any way, you pass it in a normal biological cycle, it does not react with your body. So Krypton 85 is the safest of the radioisotopes available for this application. Yes?
What's the ultimate power production given the available Krypton 85?
The question was, what's the ultimate power production given the available Krypton 85? That could be easily calculated again from the information I have, but I got to point out that Krypton 85 is currently produced in such quantities that the electric power plants are dumping 50 kilocuries of Krypton 85 into the atmosphere per gigawatt hour electric generated, and that accounts for only that is only 15% of the total Krypton 85 production. The point being that we're currently generating lots of Krypton 85. It is one of the three major waste radioisotopes, and there is a very large stockpile in this country alone.
What's the half-life?
9.8 years is a half-life of Krypton 85.
Getting back to the home unit.
Okay.
Just a ballpark estimate as to how big would you envision a unit of power at home?
Okay. Well, the question was is something on the order of 15 kilowatts. How big do I envision that? The answer is that, of course, we haven't built anything of production size yet. But the prototypes that we built in that power range, the core itself, without any cooling, is about 10 by 11 inches. So it's very, very compact. Weighs about 300 pounds. But of course, once the technical issues are solved for that device, it would have to be immersed in some kind of an oil bath and a tank with heat sinks, or may require a circulating fluid for cooling, but the heart of the unit itself is very, very compact. Yes?
You mentioned resonance problem at the beginning of your units there. Is that a problem for all of them, and have you solved the problem?
Okay. The question was that I mentioned some of the resonance problems that we have with this technology, and is that problem inherent in all the designs? And the answer is that the problem is a frequency drift problem combined with the fact that the fundamental oscillation frequency doesn't remain. I mean, the picture I showed with a very clean signal is an initial signal. Over a period of days, harmonic setup and a lot of noise shows up in that signal, and it diffuses the energy through a spectrum so that it's out of phase and not readily collectible by our design. That problem has been inherent in all the larger devices, whereas the small devices don't suffer from that problem. I am out of time. I see I'm being rushed out of here. I will be available for anyone that has further questions. I do have just a handful of copies left of my talk on this table here if anybody wants them.